All right, so 2023 AP Stats. This test was only 3 days ago, and we already got the questions. So let's do them. We're not going to check our answers. We're going to watch our time. So let's go. As part of a study on the chemistry of Alaskan streams, researchers took water samples from many streams with temperatures colder than 8 degrees Celsius and from many streams with temperatures warmer than 8 degrees Celsius. For each sample, the researchers measured the dissolved oxygen concentration in milligrams per liter. These are the colder ones. Let's circle that so we don't miss it. The researchers constructed the histogram shown for the four dissolved oxygen concentrations in streams that's colder than 8 degrees. Based on the histogram, describe the distribution of colder. Lovely. So here's what we're going to do. We got socks. So at first, we're going to describe the spread. So with spread, that means we want to do range. So we're going to say the range, and then we'll throw in this word salad. We might copy and paste it. That'll save us time. So the range of dissolved oxygen in the streams with temperatures colder than 8 degrees is about, we'll throw in about because we don't know, like that 2 to 3 one, it's 2 to 3. We don't know that it's 2. But we'll say that it's about 2. So, or we could say between. Let's do that. So we'll say the maximum is from 2 to 14. So the maximum is 12. The minimum is from 3 to 13, which is 10. So the range is between 10 and 12 degrees. No. 10 and 12 milligrams per liter. Lovely. Outliers. There may be outliers. There may be an outlier or two in the 2 to 3 milligrams per liter bin. And 4 to 5 milligrams per liter. Maybe. There may be. Okay, next, center. They want us to find the center here? Okay, so we'll go median. That won't be too bad. They don't give us a total count of streams. Hang on. We get a calculator. Am I really going to do that? I suppose. So, we got... Shoots. We got 3, and then 13, and then 12, and then 15, and then 40, and then 94, and then 117, and then 89, and then 46. So there's a total of 429. That's my birthday. And that means we're looking for the plus 1 divided by 2. We're looking for the 215th data point. So then we have to count up to 215. So we'll start from the right and see that that's definitely going to fall in between 11 and 12. So we'll say the median. So we don't need to do the context actually again because we did it so hard in the beginning. So we'll just say the median is between 11 and 12 milligrams per liter. All right. And then the shape. So the distribution is definitely skewed. The distribution is skewed to the left. It's to the side that the tail is on. All right, that's everything with that. So that took a long time, so we're just going to go ahead and move on. Make sure we got everything again. We did the context in the beginning. So that's fine. B. Oh my gosh, we got to draw stuff. We got to draw a box plot. Well, let's make sure we were actually correct with our median. Whoa. No, this is the other data. The researchers computed the summary statistics in the table for dissolved oxygen concentration in streams for the sample warmer. Right, so now we need to draw a box plot. Do not indicate outliers. Oh, okay. That was the first thing I was about to say, is that we'll have to do the outlier, but we don't. So how do we draw a box plot? We go to the median, and it is a little less than 5.5. So see how this is? That means we're looking like there, because that next line is 5.5. Okay, and then we go to Q1. It's a little less than 4.5, a little more or less than the other one was, probably like here. And then we go to Q3, which is a little more than 6, like right here. And then the max, is 13.45, all the way up here. And then the min is 4.39. Whoa. Wait, no, the min is 2.1. Right about here. So then to complete it, you do that, you do that, you do that, and you do that. Right, so the problem is we're not going to be able to indicate outliers because we don't know the specific thing. But that we can definitely say that that max is going to be an outlier. Surely they'll have us do that. 1.5 times IQR. IQR is only like 1.5, so 1.5 times 1.5, it's 2.25. And so that max is definitely above that like 8.6 threshold. Okay. The researchers believe that streams with higher dissolved oxygen concentration are generally healthier. What is going on? Are generally healthier for wildlife. Which streams are generally healthier for wildlife? Those with water temperatures colder than 8 degrees or those temperatures warmer than 8 degrees. Using characteristics of the distribution of dissolved oxygen concentration colder than 8 degrees and characteristics of the distribution warmer than distribution. Yeah. So many words that they have to use. Okay. So we're mainly just going to be looking at the medians probably. And we even calculated the median of this already as 11 to 12. Wait, the colder water has more stuff dissolved? Oh yeah, I forgot that that's like the weird inverse, because hotter water like dissolves more solids, but colder water dissolves more gases. Okay. So what do we want? We want higher dissolved concentration. Dissolved oxygen. So we look at the median, we say that's 5.4. And this one's 11.12. Yeah, so that's pretty clear. The colder waters are better because they dissolve more oxygen. That's not a scientific thing. That's like a statement we're now going to back up. We see this because the median dissolved oxygen I missed the dot on the I. Is between 11 and 12 milligrams per liter while the warmer than 8 degrees is 5.4 milligrams per liter. Hang on. Let's make sure the units are the same. Do they say that it is? Yeah, well, they just say they use the same units here. That would have been dirty if the units were different. Okay. So, what then? I'm going to throw in a little quick 11 to 12 milligrams per liter is greater than 5. Or no, we'll throw in a little more sensible statement than that. I'm sorry it's taking me so long to write these words. So the colder streams have a median with twice as much oxygen. That was so many words. That last sentence isn't very good. So the colder streams have a median with twice as much oxygen dissolved. Yeah, that's characteristics of the distribution. That's pretty much exactly what they want. All right, cool. 12 minutes. How much time are we supposed to spend per question? An hour 5 divided by 5 is 21. So we're looking pretty good. Is that true? It's not true, is it? It's 13. So we're looking less good, but still good. All right. A developer wants to know whether adding fibers to concrete used in paving driveways will reduce the severity of cracking, because any driveway with severe cracks will have to be repaired by the developer. The developer conducts a completely randomized experiment with 60 new homes that need driveways. 30 of the driveways will be randomly assigned to receive concrete that contains fibers, and the other 30 will receive concrete that does not contain fibers. That sounds pretty good. After 1 year, the developer will record the severity of cracks in each of the driveway on a scale of 0 to 10, with 0 representing not cracked at all and 10 representing severely cracked. Based on the information provided by the developer's experiment, identify each of the following experimental units. So, severity of the crack. So a lot of times I kind of like to start with like the response variable and the treatments, and then that helps you think about exactly what the experimental units are. Although I don't think it's as hard here. I'm thinking about like that insect in the box one, because experimental units was the middle one there. Anyway, so response variable, what are they measuring? The severity of the cracks in the driveway on a scale from 1 to 10. I'm not sure if we have to include that, but it definitely won't hurt. The treatments, we have 2 treatments. We're doing fiber in the concrete and no fiber in the concrete. So what is our experimental unit? Our experimental unit is each driveway, right? It's like we won't say the house, but it's the driveway, really. Yeah, each driveway. Okay, we don't need to think too more about that. Describe an appropriate method the developer could use to randomly assign concrete that contains fibers and concrete that does not contain fibers. So we normally put them all in a hat. That definitely makes it harder for this one. So let's just assign them letters So we'll say, oh my gosh, I really do like drawing him out of a hat though. So let's number each driveway 1 through 60. Number each driveway 1 through 60. No. We're not straying from the tried and true. We're going to say put, well, we'll stray a little bit. Put a picture of each house in a hat and draw out 60 in a hat. Let's throw in a little more just for some pizzazz for anything else. Shake well and draw out 60. Assign these to have either one of them. Fiber in their driveway. The rest to not contain fiber. And that is great. Yeah, that will suffice. Put a picture of each. We will change property because they're building these houses, right? So there might not actually be a house there. Put a picture of each property in a hat, shake well, and draw out 30. Oof. There's a total of 60. Draw out 30. Assign these to have fiber in their driveway and the rest to not contain fiber. Beautiful. Next. Suppose the developer finds there is a statistically significant reduction in the mean severity of cracks in the driveways using concrete that contain fibers and compared to the driveways using concrete that do not contain fibers. In terms of the developer's conclusion, what is the benefit of randomly assigning the driveways to either the concrete Do we just say that you can't draw a conclusion? You can't draw a conclusion if it's not randomly assigned. And then we'll include a quick little context bit too. So we would say something like, houses in certain areas I mean, are they all in the same town? Does it say that? Oh, also there are already new homes. We can still say properties though. Houses in certain areas might get different weather or get used harder. You need to make sure everyone is represented. Well, what? Do I need to say something specifically about higher? Or I'll say you need to make sure everyone is represented. Every driveway, I guess I should say. Every location. Oh my gosh. Represented. So then you have to make a specific claim about like if this would be higher or this would be lower. So you need to make sure every location is represented. So if there was not random assignment, maybe all the driveways with fiber were in, I guess, temperate climates. Causing them to not crack. And show wait, which way was it? And show that the mean crack severity is low. So many words to say such a small thing. All right. Next, how are we looking? Where should we be? We should be at 26. We're at 22. Beautiful. Bath fizzies are mineral tablets that dissolve and create bubbles when added to bath water. In order to increase sales, the Fizzy Bath Company has produced a new line of bath fizzies that have a cash prize in every bath fizzy. Let the random variable x represent the dollar value of the cash prize in a bath fizzy. The probability distribution of x is shown. Oh, that's fun. That's very fun. Based on the probability distribution, answer the following. Calculate the proportion of bath fizzies that contain $1. Oh, I was going to say, is that not just in the chart? But no, we have to... Wait, they all have a cash prize, every one of them? In every bath fizzy. Okay. Wow, these are going to be expensive then. Okay. So the idea is it's in all of them. So we just have to do 1 minus 0.2 minus 0.05 minus 0.05 minus 0.01 minus 0.01. And so what is that? Well, that's 1, so then that's 3. So then 3.2, so it's 1 minus 3.2. So 0.68. I don't know why I'm not feeling very confident, so I'm going to put that on the calculator. Of course. Okay. Calculate the proportion of bath fizzies that contain at least $10. So which way do you need to go? So as we won at least $10 means that the least amount is $10. So we're going to do 1 minus 0.2 minus that 0.68 that we just calculated. I'll be more confident here and say that that is 0.12. Except I did just accidentally open that. So now that it's open, I will type that in and confirm that that is 0.12. B. Based on the probability distribution of x, calculate the probability that a randomly selected bath fizzy contains $100, given that it contains at least $10. Okay, that's easy enough. So we pop a little, what is the probability of $100? 0.01 out of the probability of at least $10, which conveniently we just calculated. Look at it again to make sure. My goodness, that would have been actually far easier to just add those together and see that it's 0.12. But anyway, it's all good. 1 divided by 12, not sure. So we'll type that in. That is the same as 1 divided by 12. You could also, of course, 0.01 divided by 0.12. and see that it is about 0.083. I'll do that. Equals 1/12, approximately 0.083. Actually, why not do that? Lovely. And that's a formula, so that's plenty of work. Based on the probability distribution of x, calculate and interpret the expected value of the distribution. Yeah, this is what I knew was going to be fun. So we'll show work as well, unfortunately. We'll write it right here, though. So we'll do 1 times 0.68. See, here we just do all these. This is where you just do all these multiplication. There's the probability of winning $1 is 0.68. The probability of winning $5 is 0.2. Probability of winning $10 is 0.05. Probability of winning $20 is 0.05. Probability of winning $50 is 0.01. Probability of winning $100 is 0.01 as well. And so now we just got to calculate all of this out. Do we need a calculator to do this? Was it quicker with one? I don't know. So we got 0.68. 0.68. We got 1. We got 0.5. We got 5 times 2. We got 10. We got 0.1 times 5. We got 0.5. And we got 1. Love it. That's actually fine. So that's 1. That's 2. That's not 0.1. That's another 1. So we got 1, 2, 3, 33. Wait, that's not 10. That's 1. 4.3. Okay. I don't want to get these wrong. So I should have just done this in the first place. But also, every time that I've come to the calculator to check my answer, I've been correct. So and if I get an answer different than what I calculated, I'm going to be very suspicious. Oh, how did I say 3? No. Yeah, it's 4.68. Okay, I'm not suspicious of that. Yeah, $4.68. So that's your expected value. And that is plenty of all the work that we need to do. D. The Fizzy Bath Company would like to sell bath fizzies in France, where the currency is euros. Suppose the conversion rate for dollars to euros is $1 to 0.89 euros. When was that? This is like the pricing method of charmed aroma bath bombs and stuff. Well, this is if they have like $1 prize inside. This is more like the pricing for lottery tickets. What is the dollar to euro? Holy moly, that's exactly what it is. I guess that's pretty consistent. Actually, no, it's not at all. Well, no, it's not consistent at all, but it's exactly right now. Interesting. Okay, anyway. The Fizzy Bath Company would like to sell bath fizzies in France where the currency is euros. Suppose the conversion rate for dollars is use your expected value. Calculate the expected values in euros. A little chemistry here, a little dimensional analysis. That seems a little strange. We're simply going to do $4.68 times 0.89 euros over $1 to show that we will do 4.68 times 0.89. 4.17. Roughly 4.17 euros. Lovely. Wow. Number 4 already. Okay. We're only 30 minutes in. A medical researcher completed a study comparing an omega-3 fatty acid supplement to placebo in the treatment of irritability in patients with certain medical conditions. 19 patients with medical conditions volunteered to participate in the study. They always had to volunteer though. The study was conducted using the following weekly schedule. Each patient took a randomly assigned treatment, omega-3 supplement, or placebo. The patient, week 1, each patient took a randomly assigned treatment, omega-3 supplement or placebo. Week 2, the patients did not take either the omega-3 supplement or the placebo. This was necessary to reduce the possibility of any carryover effect from the assigned treatment taking 1. Okay, so the first week they took stuff. The second week they didn't at all. The third week, each patient took the treatment that they did not take during week 1. What? Why? At the end of week 1 and week 3, each patient's irritability was given a score from 0 to 10, with 0 representing no irritability and 10 for each patient. The 2 irritability scores and the differences in their scores, placebo minus omega-3, were recorded. The results are summarized in the table. Oh, so they tested both of them and gave them time off. So then they measured everybody with each. So there was 19 people total. They just were randomly assigned to take one first. With the placebo, there was a wide range. Okay. They're just going to make us do a test. Yeah. The researcher claims omega-3 supplements will decrease the mean irritability score of all patients with the medical condition. All patients with a medical condition similar to the volunteers. Is there convincing statistical evidence to support the significance claim? Well, they can never say all. So I'm going to say even after the calculations. I mean, for one, is that the difference per patient? 2 irritability scores and the difference in their scores were recorded. Even after the calculations, you could never claim that it would decrease it for all. But we will run the test nonetheless. So we're looking for, I mean, we should run the difference, right? So if I subtract those two values, those would be the same. Yeah, okay. So it's definitely still a 2 sample. But we have the placebo for the difference. So we need to say, we'll go with X. So we'll say X equals the average difference in irritability. It's the average difference in irritability, or the average. I mean, what did they do? Placebo minus omega-3? Wait, what? For each patient, the 2 irritability scores are posted. So they did placebo minus omega-3. So if placebo was bigger, oh yeah, higher irritability. Yeah. So X is the average I'll just say exactly what it is. Difference in irritability between taking placebo and taking omega-3. Average difference in irritability between taking placebo and omega-3, parentheses, placebo minus omega-3. Irritability level. Okay. Then we're going to state that we're going to do a 2... I'm going to throw in a little for the population, just to be clear. So we're going to do a 2-sample T, let's not forget T test for means. Oh gosh, did I ever figure out how to do the degree of freedom if it's a 2-sample? I'm not sure. I'm going to change colors though for sure. I'm going to set up our null hypothesis is that X is equal to 0. Do I need to set up 2 different variables? You normally do, right? This is kind of weird. So our null hypothesis is that X is greater than 0 because omegas are higher. I really shouldn't have to, though. I just had to make sure I'm doing it for difference. So I am clear, especially weird how I'm setting up my null hypotheses. I feel like I do definitely have to be clear that I'm doing a 2-sample. But I was clear that I'm doing a 2-sample. So that's good. Now I'll say that I never know what to do here. Hat is sample, right? I can say X hat is I thought they would use hats on those formulas. Right, it's these formulas I'm looking for. They do. Oh, they use pointy hats. Well, let's use pointy hats then. Well, it's for mean. Oh yeah, no, here they use bars. Okay. So let's do, I mean, I know how to do it. I don't even need the formulas, really. It's 1.789 because they just give it to us. But we can't use this standard deviation, right? I was going to have to calculate it because it's 2-sample. I feel like we have to calculate it. Because we're doing like the sampling distribution here. Is this a 2-sample? Or is this a 1-sample actually? Doesn't say, does it? It's really just a 1-sample, isn't it? But no, because they're calculating it. That's tough. I might look that up later, see what other people think. I think it's going to be a 2-sample. I'm going to run it as a 2-sample. And I'd like to pool it. Is that even an idea? If I had a formula, I'd pool it. There is no formula for that. So we'll just use this. Standard deviation 1 squared over 2. So we'll do the square root of 2.987 squared over 19 plus 1.739 You know what? I think this is all wrong. Because this has got to be with independent populations. These populations are not independent. And what you're measuring is the decrease. This is a one sample. This is a one sample. It has to be. It has to be a one sample. X is still the average difference. But it has to be a one sample. It's a one sample because it's not with two independent populations. They're giving us like two samples, but it's got to be a one sample. It's with one. It's not with two different populations. It's only with one population. And what are we measuring? What are we trying to talk about? We're trying to talk about the decrease. So we need to, and they're with the same person. So we have the measurement on that. This is the one that we're going to use, 2.485. We're going to go 2.485. What is it? Just that? Well, so it's that over the square root of n. Is that right? Judging off the last one, that's right, but I'm going to make sure. Yeah. It's got to be a one sample. I hope I'm not going to regret questioning myself. So we'll go with S equals that. And then they want us to calculate a z-score. So oh wait, now I'm liking. This is still 0. Well, that's not 0. That's the sample. So then when we do our z-score, right, so they do want us to do these calculations. There is generally a point for the z-score, even though you shouldn't need to calculate it. But we'll calculate the z-score just to make sure. So 2.485 divided by the square root of 19 is roughly 0.57, pretty close to 0.57. And then we need to do, so z, what is it, z star? It's not z star. We'll just call it z. Z is that value, 1.789, divided by 0.57. 1.789 divided by 0.57. So that's very far off. That's very far off. And you know what? Let me actually do 1.789. Oh, those are in order. Divided by that. Okay. Much more confident with the 8, actually. Okay. So then we just got to run a norm CDF. We just got to run a norm CDF. And we're trying to show one way. We're trying to show... Should we throw that in here? One sample. Let's throw it back here. One-sided. Ooh, I'm glad I came up here. Because remember, I very much said it. We're not doing a z-test. We're doing a t-test. So we need a degree of freedom. Which actually, thank goodness, because then I know what the degree of freedom is. The degree of freedom is 19 minus 1 is 18. So then we've got to run a z-test. I don't remember what it's called on like other calculators, but I obviously know how to do it here. is not in stats, but is in distributions. And we go down to a student's T, and we say our degree of freedom is 18. So I'm not going to do the calculator notation. I'm going to do, say, T distribution, DF, 19. Let's draw our curve. It's very similar to a normal curve. And what do we want? We want, what is the probability that it's that or greater of 1.789? Oh, wait, do I just need to use the z-score here? Do they not let me change all the other stuff? I guess not. Of 3.138? That's very small. 0.002. It doesn't seem like that should be the case, though, does it? That is a massive standard deviation. I didn't make some wrong calculations, did I? What's the square root of 19? It's about 4? Yeah, it's about 4. That's very surprising based on this evidence. Well, because the outliers, right? That's kind of what the long tails are probably showing. Okay, whatever. Yeah. So we're trying to show, let's show that that's 0. And we're trying to find this area where this is 3.138. And we go P is approximately 0.00284. Lovely. Now we'll change colors and we'll zoom in and we'll say because 0.00284 is less than, or we'll say P equals is less than the sig level of 0.05, we reject the null hypothesis. There is evidence that that you will that there is evidence that who did they get to volunteer? Oh, somebody with a medical condition. There is evidence that patients with this medical condition will have lower irritability levels after taking omega-3. And then real quick at the bottom we'll say still he should not say for all patients as there were patients in the study it didn't work for. Interesting. Nice little question about medical stuff, honestly, as long as I answered it right. Is that there's definitely decently strong with 0.002 p-value that taking omega-3 makes you less irritable. However, we look at the data and we look here and we see actually 25% of people. Let's actually specify that because that's brutal. 25% of people it made worse. For 25% of the people, it was worse. Okay, we took way too long on that one, I think. Well, we got 15 minutes for number 5. Wildlife biologists are interested in the health of tall elk, a species of deer found in California. An important measurement of tall elk health is their weight. The weight of a tall elk is difficult to measure in the wild. However, chest circumference, which is believed to be related to the weight of a tall elk, can easily be measured from a safe distance using a harmless laser. A study was done to investigate whether chest circumference in centimeters could be used to accurately measure the weight in kilograms of male tall elks. For the study, wildlife biologists captured 30 male tall elks and measured their chest circumference and weight, and then released the elk. The data of the 30 male tall elks are shown in the scatter plot. Lovely, lovely. And then I bet we got a little computer thing. No. Okay, looks like they might just tell us. Describe the relationship. Ooh, we got another describe, but this is not a histogram. When you describe a linear thing, you go DOFS. Another great little acronym. So it stands for direction. Well, we'll throw our context in here as well. So we'll say the bigger the chest circumference, throw in a little on average because you gotta. The bigger chest circumference, the heavier the elk. Or should I say the male tall elk? Okay. Outliers. There seem to be no outliers. Form, it seems to be linear. Quite strong relationship, frankly. Let's say strong. I think that's good. I think that's fine. I got my context in. I got all my DOFs. Once I get context in the first one, I'm good. Following the equation of the least squared regression lines relating the chest circumference and weight for the male tall elk, the weight of one male tall elk with a chest circumference of 1.48 is 204.3. Using the equations of the least squared regression line, calculate the predicted weight for this male tall elk, showing your work. Lovely. So the predicted weight, we just got to plug it into the calculator. And we got to do negative 350.3 plus 3.7455 times the chest circumference, 145.9. We simply go for it. They're going to ask us to interpret the negative y-intercept probably too. 145.9 times 3.7455 minus 350.3. Boom. 199.91395 kilograms. That's the predicted value. So they told us what it weighed, but that's the predicted value. That's pretty good. Calculate the residual. The residual is 204.3 minus the 199.91395. So we'll bring the calculator back. 204.3 minus the answer, 438. Yeah, lovely. Kilograms. That was simple. Next, the equation of the least square regression line rating the chest circumference of the weight is repeated here. Thank you. Interpret the slope. Love it. So this is a fill in the blank sentence. So we say, on average, for each increase of 1 on the x variable, which is chest circumference, so 1 centimeter of chest circumference, a male Toll elk will weigh 3.7455 more kilograms. On average, for each increase of 1 centimeter of chest circumference, a male Toll elk will weigh 3.7455 pounds. Yep. The sambar, another species of deer, is similar in size to the Toll elk. The slope of the population regression line relating to chest circumference is 4.5. A wildlife biologist wants to determine whether the slope of the population regression line from male Toll elk is different than the male sandbars represent the slope of the population regression line from males. The hypothesis, the test statistic was calculated to be 3.4. Assume all conditions were met. Determine the p-value. Okay, so this was something that was not done in my second year because of COVID, and I really think that was also something they added that year, and so it was not in the year before. I might be wrong, and I just didn't teach it, because I do think that formula was here. But I'm hoping... Well, these are just formulas to calculate that. I mean, they use the word test statistic. I feel like that just means I just gotta do a normal curve. Oh, but I gotta know like the dimensions of the normal curve. Okay, what are these formulas? Let's just copy the whole box down here. Okay. Determine the p-value. So I suppose... I mean, Numworks will run tests and inference by doing tests and doing slope. Ooh, slopes are t-tests? I think it'll tell me the p-value. Wait. The null hypothesis is not that it equals 0. Maybe we don't actually use the slope stuff here. Can we just do it as a 1 sample? Well, what are those formulas? I mean, this is just a 1 sample. But we're comparing it to 4.5. So the mean is just the B. Yeah, that makes sense. That the mean of B is 4.5. And then the sampling, that's what we want, is the sampling distribution. Whoa, where the standard deviation of x is that? Well, yeah. But how do I get the... It's the test statistic. So they tell me the sample size. They calculated the test statistic, which was the mean divided by... Oh, wait, since they calculated the test statistic, I can just do 0 to 1. Because they already calculated the test statistic. So I just have to do norm CDF from 3.408 to infinity of 0 to 1. Because they already calculated the test statistic, not from 0 to 1, with a mean of 0 and a standard deviation of 1 and an upper and a lower. And we put that in, not here, but in distributions. And we got to go back because we got to use the normal distribution with a mean of 0 and a standard deviation of 1. And we're looking on the upside, actually, starting at 3.408. Boom. Very small. 0.003, right? Because it's 3.2. We're going 1, 2, 3, 4. Ooh, one more 0. I mean, that slope was 4.5. This slope was 3.7. And what was the sample size? Well, 30. I suppose. At a significance level of 0.05, what conclusion should we draw? I feel like I'm doing one of these wrong. So I'm surprised we're rejecting on both. We should reject the null hypothesis. Because our p-value of 0.0003 is less than 0.05. There is evidence. We actually need to find that on both sides, right? So we should multiply that by 2. Because it's two-sided. Yeah, that's what they were getting at here. It's two-sided, so we have to multiply that by 2 because you got to look at both tails. Still less, though. Still significantly less. We'll still pop the 0.06. There is evidence that the slopes are different. I kind of think I did it wrong, though. I feel like they wanted it, if you just did it one-sided, they wanted it to, they wanted there to be a significant, but if you did two-sided, they wanted it to not be a significant. I think. Or something like that. Well, shouldn't that go the other way? Anyway, I think we're good on that. So we popped the minute 05. That's great. Now we're on to 6. So I've heard Cleo and her gold necklaces. A jewelry company uses a machine to apply a coating of gold on a certain style of necklace. The amount of gold applied to a necklace is approximately normally distributed. When the machine is working properly, the amount of gold applied to a necklace has a mean of 300 milligrams and a standard deviation of 5 milligrams. A necklace is randomly selected from the necklaces produced by the machine. Assuming that the machine is working properly, calculate the probability that the amount of gold applied to the necklace is between 296 and 304. Cool. Close to 68. They've been toying with that 69 a couple times on this test. So let's go for it. We got to do 296 to 304 with a mean of 300 and a standard deviation of 5. And we label everything since that's what we have to do. And that is approximately, Go back. Mean of 300. Standard deviation of 5. Next. Looking between 296 and 304. Boom. Quite far off from 69, actually. 0.576. Yup. This jewelry company wants to make sure the machine is working properly. Each day, Cleo, a statistician of the jewelry company, will take a random sample of the necklaces produced that day. Each selected necklace will be melted down and the amount of gold applied to that necklace will be determined. Because a necklace must be destroyed to determine the amount of gold that was applied, Cleo used random samples of size n equals 2 necklaces. Cleo starts by considering the mean amount of gold being applied to the necklaces. After Cleo takes a random sample of n equals 2 necklaces, she computes the sample mean amount of gold applied to the 2 necklaces. Combined? Or each? Suppose the machine is working properly, with the population mean amount of gold being applied of 300 milligrams. Like they said. Calculate the probability that the sample mean of gold applied to a random sample of n equals 2 will be greater than 303. So it's hard for us to use the formulas, right? Because the sampling distribution idea requires it to be normal, and you can't really do that with n equals 2. So I feel like, and that was their little hint by giving us this as a start off. It's between 296 and 304. What's the probability that the mean will be greater than 303? Can you even do that? Is that even like... Not sure how that's possible. Exactly. Or am I just psyching myself out because I know this is supposed to be the hard question? It's just weird that it's a mean. So... No, I don't think you can just use the sampling distribution formula. I feel like you have to do a probability type of thing. Oh no, do we have to think about the adding and subtracting means and stuff? So it's actually just kind of all the same, right? So we know the mean of the mean is, or I guess the mean of the sample, maybe we just go X bar, is 300. We're going to say 300 plus 300 over 2. Yeah. And so then to get the standard deviation, you have to do like the same thing, except for to add them, you have to square them and stuff, don't you? You can't just add standard deviation. You have to 5 squared plus 5 squared. Oh, right. That's the idea. If you really are just multiplying them, then you can. But since there's 2 different things we're bringing together, that's where you have to do like squared, like Pythagorean theorem ideas. And then we divide them by 2. That's a weird one. I really do think that's right, though. So what is that? That's 5 root 2 over 2. Just 5 over root 2. Yeah. And now I should be able to do a normal distribution with that, right? That's kind of wacky stuff, but that is what you're supposed to do on question 6 stuff. I would love to check my answers, though, with somebody who knows what they're talking about afterwards. So a norm CDF from 303 to infinity with a mean of 300 and a standard deviation of 5 root 2 over 2. With a mean of 300 and a standard deviation of 5 over the square root of 2. And we want from 303 to infinity. 0.198. I guess that's fair. 5 is a large standard deviation in terms of, I mean, it's not because we're at 300, I guess, but yeah, anyway. Suppose Cleo took a random sample of 2 necklaces that resulted in a sample mean of gold applied of 303. Would that result indicate that the population amount of gold being applied to the machine is different than 300? Justify your answer without performing. Right. No. Assuming it is 300. Wow, we had to do 3 inference tests. The probability of getting a sample mean this high or higher is 0.198. Generally, this should be less than 0.05, and this is much higher. And then we need something like doing this process she will get a sample this high. Well, I guess I already said this. I just wanted to be more specific. About 1 out of 5 times. Okay. I like it. Next. Now, Cleo will consider the variation in the amount of gold applied to the necklaces. Because of the small sample size of 2, Cleo will use the sample range of the data for the 2 randomly selected necklaces rather than the sample standard deviation. Cleo will investigate the behavior of the range for samples of size n equals 2. She will simulate the sampling distribution of the range of the amount of gold applied to the 2 randomly sampled necklaces. Cleo generates 100 random samples of n equals 2 independent values from a normal distribution of the mean of 300 and a standard deviation of 5. The range is calculated for the 2 observations in each sample. The simulated sampling distribution of the range is shown in graph 1. So these are of a whole bunch of ranges. So you see a range is like averages, maybe not average, medians around 0, which is what you'd expect because they're coming from the same machine. And then it tails out. That all makes sense to me. Wait, what's graph 2? The process is repeated using a standard deviation of 8 as shown in graph 2 and a standard deviation of, we got 5, 8, and 12. So 5 is what they told us. 8 is higher, obviously. And then, 0. So only 4.04 of them were the same. Here, 12% are the same. Wow, okay. So describe the sampling distribution of the sample range for random samples of size n equals 2 from a normal distribution with a standard deviation of 5. Got it. Describe the sampling distribution. Doffs. No. Socks. So we go the center. Or no, it starts with the spread. The spread, can we zoom in here? Right about here. Right about like 23. from 0 to 23. The range of, oh goodness gracious, the range of sample ranges. We need a context somewhere too. Okay. We got, there are no outliers. We got the center here. Should we add up and try to get to 50%? So it's like 11. Oh, here. These combined. These are all 33. This is 43. So the median is going to be here. Here. So this is 1 off, 2 off, 3 off, 4 off, 5 off. So the median is 5 different. The median of the ranges was 5 milligrams. Yes. Shape, the distribution, the sampling. Here's my context. The sampling, distribution of sample ranges for two numbers randomly picked from a normal distribution is skewed to the left. Wait, so does that mean I was off base here if it's going to be skewed to the left? I don't know. Okay, describe how the sampling distribution... How much more is there? One more page after this. Okay. Describe how the sampling distribution of sample ranges for samples assigned n equals 2 changes as the value of the population of the standard deviation increases. So the range increases. The median also increases. But it stays skewed to the right, which is actually what I should have set up here. I get my rights and lefts confused. When I picture the political right, I always picture him on the left. Yeah, it stays skewed to the right, always. Recall that Clio is considering both the mean and the standard deviation of the amount of gold applied to the necklaces to determine whether the machine is working properly. Suppose that 1 month later, Clio is again checking the machine to make sure it is working properly. Clio takes a random sample of 2 necklaces and calculates the sample mean in gold applied as 303 and the sample range as 10. Recall the machine is working properly if the amount of gold applied to the necklaces has a mean of 300 and a standard deviation of 5. Consider the range of 10 from the sample size of n equals 2. If the machine is working properly with a standard deviation of 5, is the sample range of 10 milligrams unusual? So here's what we do for that. You go up to the one where we use, and we go to 10. And we have to add up all of these. So it's not that bad because you see how that's 0.04, that's 0.02. So no, it's not. No. Look at, did they label these? Yeah, graph 1. Look at graph 1. The cumulative probability of getting 10 milligrams or higher for the range is greater than 0.05. I mean, what is it about? It's pretty low. So it's like 0.05, 0.02, another 0.02. It's probably about, I'll say between 10 or 15%. Though it will only happen between 10 and 20% of the time. Yeah, 0.04 plus 0.02 plus 0.02 plus 0.02. Okay. Do Clio sample mean of 303 and range of 10 indicate that the machine is not working properly? Wait. No. No, they don't. This is the range of 10. This is the one. Yeah, it's 10 or worse. So it's 10 is below 0.04, but you've got to look on the right side. No. As I said before, I feel like that's the same thing. As said above, this sample range or higher would occur 10 to 20% of the time. Which is not below the typical threshold of 5%. That was it. That's fine. Finished with 6 minutes to spare. So maybe I'll pause the recording and find some answers and see how mine agree. So here is the first mistake that I found that is definitely a mistake. It's more of a just forgotten though. So I didn't realize that they asked us to interpret the expected value. But that makes sense. And so I won't rewrite it for myself. I'll just read what he said. For repeated bath fizzes, the average amount as a cash prize is 4.68. Yeah, you could just say the average amount of the cash prize is 4.68. Yeah, I agree with what he said. So I just didn't read the question enough. I was trying to rush. I don't know. That's a little P for that part, but I'll take it. So I didn't do the conditions for this test. I was so caught up on determining what type of test it was, and they went with matched paired test. I forgot that was even a thing. I forgot to check the conditions. That makes sense though. That does make a lot of sense. You've got to do the conditions. So let's see what they found. They did find the exact same p-value. They did the exact same math. They never specified what their degree of freedom was. and they never showed how they calculate it. I do not like their work, and they don't even specify that they reject the null hypothesis. I do not like the work that they give, but I was wrong about this. But I got the exact same answer that they had. He got 196 for this somehow. So I wrote down the exact same work that they did. So I must have typed it into the calculator wrong. I did 146.9. Oh. So I typed it into the calculator wrong. I did the math exactly right. I typed it into the calculator wrong. So I don't know what I would lose for that. I might get a P, but could tell you that I would not lose points for the residual because I did it properly and I got the right answer with the answer that I calculated. So I just typed it into the calculator wrong. Luckily for me, I wrote all my work, so I should get decent points for that. So this one I really butchered when we talked about the slopes. So I guess you did have to use the slope formulas. Does he have the formula sheets on here? Yeah. So you did have to use these things down here. And you had to end up doing a t-test. It really doesn't say to do a t-test. But yeah, like I said when I did this the first time, this was not on my last year. And I really don't think it was on the first year either. So this is not something I'm as familiar with doing, the linear regressions. COVID knocked it out of the curriculum. Also chi-squared. Luckily, we didn't have to do a chi-squared. So that is why I did that wrong. So you had to get your degree of freedom, which is 28. They did do two-sided, though. So I was right about that multiply by 2 part. I just did it as a norm CDF when it should have been a TCDF. But then I made the same conclusions, and I made correct conclusions based on my p-value. So I don't think I lost too many points. That's probably another p. So I probably got like a 3 on, what is it, 2 or 3 of these questions. You can still get a 5 with that, so I'm decently happy. So I really got all of the key bits of question 6 totally right. I may not have been specific enough on if the machine is working, because I just talked kind of about the range. I might have not been as specific about saying no, there's no way to say that the range is different or that the mean is different, so there's no way to say that the machine is not working properly. I really just repeated my answer from above, so maybe that was what really made it different. But as this guy said, this is just this guy's answers. There's no scoring guidelines, and they won't be out for a while. No, this was his work for the later stuff. Why do they even give us 2 graphs? I guess just to show the pattern. But yeah, that was it. I didn't think that question was bad. I thought question 5 was the hardest, because there's a test you don't do very often. At least I don't do very often. I thought question 6 was I didn't think there was anything really that crazy about question 6. I guess that is what they do a lot. They do a simulation of sampling distributions. At least lately, that's what they've been running a lot. So, hope that was helpful. I'd love to hear what you did if you did anything different. Everything I didn't show you, all the answers I didn't show you were just correct. So, if you got any questions, put them down below. I'd love to hear from you. So, good luck. I hope you got a 5. I'm sure you did, though.